yeah, I can run forever in those suckers. All right, so let's get to this one. No more dilly dally. So here we have 2 blocks over a pulley. And so they define our terms. We have, so block A is MA, block B is mass B. They tell us that there's no friction here, so mu equals 0, no friction. And the pulley is massless. Where does it say that? Right here. So the pulley has negligible mass. And now what's the significance of that? Well, look, if the pulley did have mass, then we would have to look at the torque, you know, the torque required to get that pulley to spin. The tensions on both sides would not be equal, right? You'd have to go like, this is T1 and that's T2. So this is if the pulley actually had mass, because to get that pulley to rotate clockwise, then T1 would have to be bigger than T2 to get that angular acceleration. But the problem starts out with the pulley being massless. So we don't have to worry about that yet. On the second part of the problem, they tell us that the pulley now has mass. But for now, there's no mass. Okay, A, I think, is very straightforward. When I first did this, I totally overthought it. They don't want summing of forces or anything. They just want, you know, a qualitative answer to what would happen. So the question is, suppose that block A had a much bigger mass. You know, so A is like this big mass, and then B is smaller, much, much smaller. Estimate the magnitude of the acceleration if A were much bigger than B. Well, the thing to realize, the net force that accelerates this system, and by system again, I mean these 2 blocks together, the net force accelerating the system comes from the force of gravity on block B. Gravity is pulling block B down. And by the way, that force of gravity is just the weight of block B, mass of block B times gravity. This is the force accelerating the system. So if block B is small and block A is big, that's going to lead to a very small acceleration. And you just want to say, because the mass of block A is so much bigger, and therefore the acceleration will be smaller. Mass A has a really high inertia. Okay. Second question is the opposite. So what if block B were really big, block B is really big, and block A is small? The acceleration is going to be really big. And again, the reason why, the net force on the system is the force of gravity on block B, which is the weight of block B, right? And then the mass of block A is very small, has a very low inertia. Okay, now we're to part B. Suppose neither block's mass is much greater, so same mass. The dots, oh, sorry, they're not necessarily equal. That's actually not going to matter. The dots below represent A and B. Okay, they want free body diagram here. Label the forces exerted on that block after release. So let's start with block A. So block A, we're going to do a free body diagram for. We'll do it right here. So block A obviously has a weight, which we're going to label MAG, mass of A times G. And it's on a surface, so there's going to be a normal force. So you could go N for normal force. Every year I do it different. Sometimes I do FN, just so it's not confused with Newton. Oh, and be careful. So block A, is block A accelerating vertically? You know, if you look at block A sitting here on the table, is block A accelerating vertically? Nope. So you want to be careful to draw these 2 force vectors the same length. And that would show that they cancel. Okay? And then the other force is going to be tension. So there's tension in the rope pulling on block A. And that's the free body diagram for block A. Now let's go to block B. So block B has weight, M mass of B times gravity. And then there's also tension. So you know what? Let me make this better. So we need, okay, I can't erase with my pen. So I'm gonna draw this longer. You'll see why in a second. So the down force is gonna be mass of B times gravity, and then the up force is tension. Now, which way does block B accelerate? Block B is gonna accelerate downward, and if the acceleration is downward, then the down force should be bigger than the up force. So notice that I drew this bigger than this, okay? And then also notice that I drew tension the same as that tension, because if it's a massless pulley, so if this pulley has no mass, that means the tension on both sides are the same, right? So you could show those tensions as being equal. We nailed it. That's that. Okay, let's go to the next part. Okay, so now we're going to derive an equation. So to derive the equation, so you want to use, so you should have this free body diagram, have these diagrams copied. In fact, you know what? I'm going to do it on this page. We're going to look at these force diagrams when we're deriving our equation. So the question here is this: derive an equation for the acceleration in terms of the masses and constants. Okay, so let's do that on this preview, because we're going to refer to the force diagrams. So let's look at, what am I doing? Okay, so let's look at our force diagram. So we're going to look at block A, and we're going to sum forces X. We could sum forces in the Y, but it's not going to matter. We're not going to be using the Y direction for block A. We only need the X direction. So we're going to sum forces X, and that's going to be T, and that's going to equal, so sum of the forces, there's only one force in the X direction. Sum of the forces always equals MA, and that's going to be mass of A. And you know what? Let me pause for a moment and make sure we're clear on our sign convention. For pulley problems, the sign convention must be consistent. So look, block A is going to accelerate this way, and then that acceleration goes around the pulley like that. So you got to be consistent with your sign convention. So up here, we're going to say plus minus, and then over here, we're going to say plus minus, right? So for block B, our sign convention is going to be down, plus, up, minus, and then over here it was plus, minus. There's our sign convention, like that. Okay, so now let's go to block B. We're going to sum forces. Down is plus, so mass of B times G minus T. Sum of the forces always equals MA, not a capital A, like that. Okay, and then now the tensions are the same. The tensions are the same because it's a massless pulley, so we just plug in right there. So we can go, I'm just plugging in. I'm plugging this into there. So we got minus MAA equals MBA. Do the algebra, solving for A. This is gonna MA. So this is what the algebra would give. Did I do that right? Let's see. Yes, so I moved this over here. I factored out the A. Yes, that's the answer. So that's what the algebra gives. And that's the answer to the question. Okay, let's go to the next one. All right, D. Okay, consider the scenario from part A 2, where the mass of block A was much less than the mass of block B. Does your equation for the acceleration of the blocks from part C agree with your reasoning? Yes, it does. Now, why? Why is the answer yes? So what we said, let's go back again. So the question here was this one. So we're talking about this one right here. So basically it's saying does this equation agree with what we said here? So if the mass of block A is much, much less than block B, that was where the acceleration was really big, right? This is where we had a really big acceleration. Now, why would that give a big acceleration? Well, because you would say the mass of A is small, and or therefore the mass of B is bigger. So we have a bigger mass of B, and mass of A is also in the denominator. So this equation definitely agrees with that. So if mass of B is larger, we have mass of B large, which is going to give us a big numerator, and then mass of A is small. It appears in the denominator being added to the larger mass. So that's going to lead to a bigger acceleration. Okay. We got one more. Okay, last one. Well, the blocks are accelerating. The tension in the vertical portion of the string is T1. Okay, so I'm just going to sketch this. So we got this pulley right here. We have, which one was A? This one was A. A, and then here's B. So, well, the blocks are accelerating. The tension in the vertical portion of the string is T1. So that's T1. Every force has an equal and opposite force. So the force on the pulley, it's the same string. So that would be T1, right? It's the same rope. So the tension acting on block B is the same as the tension acting on that pulley. Next, the pulley of negligible mass is replaced with a second pulley whose mass is not negligible. So if this pulley now has a mass, what that means is in order for this pulley to have a clockwise acceleration, in order for that to happen, the tensions on each side will not be the same. So this would be like a new tension now. This would be like T2. And to get this clockwise acceleration, that means that T1 must be bigger than T2, right? In order for that to occur, okay? So, but to stick to the variables they're giving us, so they're saying, if this pulley now had mass, well, if the pulley has mass, what's going to happen is the acceleration of the system is going to go down. You could look at that from an energy perspective, right? In this problem, we really start out with only one form of energy. Before block B is released, it starts with some height here. The only energy we start with is potential of gravity of block B, and then that potential of gravity ultimately goes into kinetic energy. Right before block B hits the ground, block B is going to have kinetic, this pulley is going to have kinetic, this block's going to have kinetic. So my point in saying this is, if we add mass to the pulley, if the pulley has mass, the acceleration of the system is going to go down, just because now there's more to accelerate. The mass of the system has gone up. So if the acceleration of the system goes down, well, let's look at block B. So the other force is the weight of block B, and we know that the acceleration's down. If this acceleration is decreasing, if the acceleration is decreasing, but the weight of block B stays the same, this stays the same. The weight of block B did not change. To decrease this acceleration, this tension must get bigger. the tension must get bigger. So the answer would be T2, which is the tension when the pulley has mass. T2 is going to be bigger than T1. And the reason why is the acceleration of the system is going to be smaller. And in order for the acceleration of block B to be less, T1 must get bigger.